Welcome, everybody. This is the first of at least 4 talks on relativity. We'll see how it goes, how quickly I can get through it, and y'all keep needing me to slow down and stop or whatever. But ultimately, the goal here is to hopefully give a better understanding of the universe we live in. This is the stuff that really got me into physics. In fact, it was a guy named Sam Allen, and I remember back in high school, who started telling me about this between classes at Bloomingdale High School and got me intrigued. And then I've just been obsessed with this relativity stuff ever since then. So 20-something years, I've been trying my best to understand this, and hopefully I can give you, at least the ways that I best understand it as it is right now. I'd like this to be something that you can use and go out in the world as a tool. I have found myself using it a lot when people have questioned me about God, because I think this really is stuff that makes you really see that there has to be a creator. It's this link of space and time. That's one of the big arguments, that you can't have time without space, and that's really what we're going to kind of get into here, is how closely linked those two things are. Okay? So, back in the late 1800s, there were 2 really big issues in physics. They thought they pretty much had everything figured out. The only 2 things they didn't really know was black body radiation. It wasn't quite working. That's just where something gets hot and it glows, and the predictions on that weren't working. And the other thing was that they couldn't figure out light. There had been some experiments that showed that light was acting as a wave, and it wasn't acting like normal waves were supposed to. So the solution that allowed us to predict the black body radiation turned out to be quantum mechanics, and the solution for the light problem is what we're going to start talking about here today, which was originally special relativity. Okay? I will try not to do too much math. There will be a little math. I won't make you do it, but it's going to be more conceptual math, like this is just what this means, and you'll see it, but it's not like you're going to get tested on or anything like that. Okay? So one of the big things about light was that there was something called the double slit experiment, where they shine light through this slit, and it went through, and it started making interference patterns, just like waves do. Whenever you have crests of waves meet troughs of waves, they cancel each other out, and this was happening on light. So they would shine light through these little slits, and they wouldn't just get a light spot and a light spot like you'd expect. They got a whole bunch of alternating light and dark bands, showing this interference that would occur in normal waves. Well, up until that point, all waves that were known had to travel in a medium. Ocean waves travel in the ocean, sound waves through the air. Every one of them had a medium. And we knew that light was traveling through outer space. It's coming from the sun to us and from other planets and everything. So there was this idea that you had to have this luminiferous ether that had to be permeating through all of space for light to propagate through. So the Michelson-Morley experiment was actually done to detect this. So if you think about, if you're on like a boat, I'm sure a lot of you have been on a boat, and you look at the waves coming off the front of the boat, they're shortened, they're compressed, and they're not going away from you as fast as the waves off the back of the boat, correct? Because you're moving in the same direction as the waves off the front of the boat, and you're moving in the opposite direction of the waves off the back of the boat, right? Have we all experienced this? Yeah? I see some nodding. Okay. And they expected that to be the same thing here. So essentially what they did was they started shining light in different directions, thinking that as Earth turned, as it orbited, as it went around the sun, that they would be able to detect us moving through this ether. And so they shined it in all these different directions, and they had a big issue, because they couldn't detect the ether. They couldn't detect any difference in the speed of light, no matter how or what direction they were shining it in. And so this got to be a very big problem, and nobody knew exactly what to do about this. there were a lot of attempts, and most of the attempts were what you might refer to as destructive attempts. They tried to break down why light would be doing this, okay? And one person came along, Einstein, who went very constructive with it. Instead of asking, why does light do this? He simply said, all right, light does this. What does that mean? What does that mean has to occur because of this? All right, so if you look at something, I don't know how familiar you are all with physics, but you can look at something like thermodynamics. All that does is look at what's happened and says, if this is what happens, these are the results. And then you have another version of it called statistical mechanics, where you actually try to go down and figure out why those things are happening. Okay? Thermodynamics, very unlikely to ever be disproven. Statistical mechanics could be very easily disproven. So these constructive ones that just say, all right, we have found this to be true, and as long as it's true, this all logically follows, they're usually very steady, very stable, and they last a long, long time. And so that's really the way we're going to get into this. In fact, I would say what we're starting with here is special relativity is probably, I just can't imagine anything even being close to it, the most well-tested theory in all of science. Every time you even use GPS, which happens quite often, especially now with all the phones and everybody has GPS, that is a verification of all this stuff we're about to go over. Because without this stuff, that wouldn't work. All right, so every time it tells you where you are, you've confirmed special relativity. All right, so postulates of special relativity. These are our two things that as long as they are true, then everything that follows is going to have to be true as well. Before we talk about the two postulates, we need to define what an inertial observer is. If you've had physics or had it with me, you should know what inertia is. And when we talk about an inertial observer, we're talking about an observer who's not accelerating. That's essentially it. Someone who isn't speeding up, slowing down, or turning. We here on Earth aren't exactly this, but we're close enough for this to work pretty well. But that's the basic idea. Just somebody who's not accelerating, but just going at a constant speed, either sitting still or moving or whatever. So the first postulate from Einstein was that the laws of the physics have to be the same for all inertial observers. Okay, you can't have them change. And the second was the big thing that no one could quite figure out why, but that it was happening, was that the speed of light in a vacuum is the same for all inertial observers. Okay? So what this means is, if, for example, you're riding in a car, and the car is going 50 miles per hour, and you get up and you throw a baseball out in front of you, and you throw it at 50 miles per hour, and someone's standing on the side of the road, how fast are they going to think the baseball's going? Car's going 50, I throw it 50. How fast to someone standing on the side of the road? How fast does that baseball look like it's going? 100, right? Well, in relativity here, if we replace that baseball with a laser pointer and light, and you get in there and you're driving a car at 50 miles per hour, and you shine the light out in front of you, the person on the side of the road doesn't see that beam of light go the speed of light that it would be if it was still plus 50 miles per hour. It's still just the speed of light. And even you in the car, when you make that same exact measurement, if you were to measure the speed of that light, you would get the exact same thing as them. Which is different, because with the baseball, the person on the side of the road is going to say 100, and you in the car think it's just going out in front of you at 50. All right, so these velocities don't add when it comes to light. It just always stays constant. All right, so let's get going with the original way we looked at how motion went. And this was through the Galilean transformations. So I think we've all heard of Galileo, right? So this guy basically came up with our equations of motions. He looked at a stationary observer and then said, hey, what are they seeing compared to an inertial observer? So the idea is, let's zoom in here so I have room, is if we have a coordinate system, which is typically just what you make for yourself wherever you happen to be. And we're gonna make this a little different. We're we're gonna make x on this axis, and we're gonna put time on this axis. So if you just stand still on this, you're just gonna simply go straight up on this as time passes. If you start moving around, then you might do something like that. If you start moving forward, or if you start moving backwards, it'll do something like that, okay? So this will be our first person perspective, and you can think of this as your own perspective, all right? And you're gonna put your origin where you are. That's where you're gonna stand, that's your x direction. But then we're interested in you seeing somebody come by. And when you see them come by, they're gonna have their own coordinate system wherever they happen to be. And we'll put t and we'll put a little prime on there to indicate it's a little different, but this is their coordinate system that they think of as just sitting still. And we'll say their coordinate system is moving off to the side relative to you at a speed v. All right, if that is the case, and then you want to be able to translate positions of objects and amounts of time that have gone by between what you're seeing and what they're seeing, to be able to tell what things look like to them, you go through what are called these Galilean transformations. And I'll just write down the simple version here, but their moving coordinate system, x prime, is just going to be x plus or minus v times t, depending on which direction they're going. And then you can do it for y, you can do it for z as well, but we're just going to only worry about moving in the x direction, so we'll leave that right there. And then as far as time is concerned, they're measuring time exactly the same as you are. All right? So we can actually break this into a matrix, and this will probably be the worst math you have to see this whole time, but I promise it's not that bad. And what happens is we can say that we can put this up into like a little matrix form that looks like this. Negative v 1, and it can act on xt, and it can give us their position and time in a vector form. Now, if you haven't taken any kind of linear algebra or anything like that, when you multiply a vector by a matrix, what it essentially does is tells you what that vector looks like in the coordinate system defined by your matrix. So if we look at this, we call this our column vectors right there, our column space. And this tells us what the two basis vectors of this new space would look like, and then you would simply move that xt amount in it, and you'd be right at x prime and t prime. And so what that does is, if we're looking at our coordinate system like this, and I'm actually gonna, well, we're gonna do it this way, x t, so this is ours. If we look at it the moment that they're right with us, what will end up happening is it's going to shift over one of their axes, which I should switch this around, I believe. Okay, xt, and then it's going to shift over one of these axes like this. Now this one is still 1, 0, so it's going to stay exactly like it was, but the other axis is going to get shifted over either left or right like that. And then that's it. You have your whole new system. You can tell what theirs looks like compared to yours. Okay? And again, I don't expect you to like crazy follow it, but just you have the idea that that axis gets tilted over. All right? And this was really good for most stuff. But when we started getting into the whole speed of light being the same, this failed. These transformations didn't work anymore. They didn't tell us that. And along came a guy named Lorentz, and he was trying to figure this problem out with that whole, break it down destructive type of method. And he came up with a set of transformations that looked different. All right, the Lorentz transformations in a very similar system or a similar situation, they looked like this. And this actually accounted for why the speed of light wasn't changing. He added this gamma term and did x minus vt like that. And then for time, it was t prime gamma, and I'll tell you what gamma is in a second, and it's t minus vx over c squared. Okay? And so the interesting part is that gamma term. What gamma actually ends up equaling is the square root, or 1 over the square root, of 1 minus v squared over c squared, where the v is the speed that you are going, and that c that we've seen shown up here is the speed of light in a vacuum, that thing that never changes, which is actually why we use a c for it, for the universal constant. Okay? And it's pretty fast. In case you're wondering, c, this value is about 186,000 miles per second, or 3 times 10 to the 8th meters per second. So that goes around our planet about 7 times in 1 second. So it's pretty fast compared to our everyday lives. This gamma makes these things change as your speed changes, which starts to scale these things differently. And if we write that down in a matrix form, it's going to look like this. Gamma, oh, and these can be plus or minuses as well. Gamma, negative gamma beta, and then, yeah, times xt equals x prime t prime. And so here, unlike before, you can, well, first off, the thing you can say is time isn't the same for these two things. For the person that's moving, they're going to see a different amount of time than what Galileo said would happen. All right, so that's really the biggest key thing you see there is time just doesn't equal time. There's a change in it. And when you do this, and we do the same sort of picture that I've done before with, we're going to put x up here and ct over here. We're going to put c times t there instead of just time. It's just a constant, but in a little while I'll tell you how that actually, well, in a little while, probably the next lecture or something, you'll find out why we do that. It just makes something really, really nice as far as how this works out. But then what happens to the prime axes is they both bend in like
What
this.
does T prime means?
Prime is the guy that's moving differently than you are. So this is a person that's moving relative to you. Okay? That's someone who's moving different to you. Now from their perspective, from the prime perspective, they think it's this. The guy that you think's moving, he thinks you're moving, and he thinks it's actually this result. All right? For him, your axis bend the opposite way that his would bend for you. Okay? And that's because we're now going to talk about why it's named this. Relativity. The idea was, since we could come up with no absolute motion through space, because we couldn't detect that ether, that how do you know who's moving? Right? You all are sitting in this room, you think you're sitting pretty still at the moment, but, I mean, are you? The Earth is rotating, we're going around the sun is going around the galaxy is going places. You know, like, who's moving and who's not? I think Einstein said does the chicken cross the road or does the road cross under the chicken? And the only reason y'all ever say that you are stationary and somebody else is moving is because you're comparing it to our planet. You know, you say, oh, I'm still relative to the planet, and then that person's moving in a car. But they have no less right to say that they're the ones that are stationary and you're the one that's moving. Okay? Because there is no way to actually go out and measure any kind of motion. If we put two spaceships out in space, the guy in the first spaceship looks out his window and sees the other one, going past him. He says, oh, I'm stationary, that guy's moving. But the guy on the other one says, no, I'm stationary and you're moving the other way. They both think the other is moving, and there's no experiment that can be done to show which one actually is correct. All right? And so that's why we get that idea. It's all relative. Okay? It's relative to what you're doing and what you have going on there. So let's get on to a light clock. And then also the great big example, this train, was one of Einstein's thought experiments, and that's actually the thing I remember Sam Allen telling me about that got me hooked on this. Okay? So, one of the problems with measuring the speed of the fastest thing that exists is you can't measure its speed in one direction. All right? So you could imagine, for example, if I were to shine a light at you, and then you, whenever the light hits you, you were going to say, all right, it hit me. Well, what's the problem with that is the light gets to you, and then I have to wait for your response to get back to me, correct? All right, and so it's slowed down by how long it takes your response to come back. So what we have to do is we want the fastest response we could get, which would be something like I shine a light at you, and you just hold a mirror up and bounce it back at me. And then I just tell when it gets back to me. But then I'm not really measuring how long it took to get to you. I'm measuring how long it took to get to you and come back. And it turns out that that's the most we can say about it. You cannot say that I know that it went the same speed on the way there and back. All right? Everything that we have ever observed could be explained by having different speeds on the way there and the way back, and they just average out to be the same speed every time. All the results would look identical if I turned the laser light on and it instantaneously appeared at your side and then came back over here at like twice the speed, so that it got here in the same exact amount of time. We cannot tell. So we can only measure a two-way speed of light. We cannot measure a one-way speed of light. We assume that it is the same on the trip there and back, but we don't know for sure. And so that brings us to making a light clock. What we're essentially going to do is put a mirror up here, and we're going to shine a light up to it, and then we're going to let it bounce back, and every time we send a pulse and it goes up and comes back, that's a count of 1. And we send it 2, 3, for however long it takes. Doesn't have to be seconds, right? Just one tick of the clock is a light going up and coming back down. Okay? Now what we want to do is we want to put this on a train. So let's say you're on a train, okay? And if this train, it's nice, it's smooth, it's going on a straight line, it's inertial, it's not speeding up, it's not slowing down. So it has every right to say that it's still. And so we're going to put somebody standing inside the train, and they're going to hold a little stopwatch, and we're going to pretend that the top of the train is so tall that they can actually time it. I mean, 7 times around Earth in 1 second isn't enough time for a human to actually time it going up to the ceiling and back, right? But pretend we have a really, really, really tall train. And so they're going to shine the light up to the mirror at the top of the train, and they're going to time how long it takes it to go straight up and straight back down. Okay? And let's say that it takes 2 units of time to do this for them. It's a unit of time up and a unit of time back down. So they look at their stopwatch and they see 2 units of time, whatever these units of time happen to be. Okay? But now let's imagine that you're standing on the side watching this train go by on the tracks. And you're standing over here and you have your little stopwatch. And you watch that light beam go up. Now, from the person on the train, that light beam just goes straight up and straight back down, correct? But you on the side, what do you see? You see it go up at an angle, hit, and come back down like that, right? And so as this train moves forward, right, you see this light beam go up, hit the mirror as the mirror is moving forward, and then come back down like this. And let's say it's going at such a speed that when you look at this, it went 1 unit distance. We can say this is 1.5 units of distance. The main point you can see here is from your perspective on the side of the road here, right, the side of the train tracks, the light traveled a greater distance, right? But everybody has to measure the same speed of light. So if it traveled a greater distance and it has to be going the same speed, and it did it in the same interval, it's the same event we're watching, what does that tell you about what your stopwatch is going to have to read? So if you drive 20 miles per hour and you're going 1 mile, and you time how long it takes you, you get that, and then you go 20 miles an hour and you drive 100 miles, what's going to be the difference in the time? Not the exact thing, just a longer or shorter. heard somebody say it. What is it?
Longer.
Longer, right? If you're going the same speed over a longer distance, it's going to take you longer, isn't it? So instead, while we're on the train, this guy, for the exact same event, he's saying 2 units of time passed. But this guy on the side, his stopwatch says something like 3 units of time passed. Or 4, or something greater. So we don't have an agreement here. Even though we've looked at the exact same event, we disagree on how long that event took. All right? So evidently here, what we're saying is, if you're moving, time is doing what for you? Here's some mumblings. What is it? Y'all can interact. It's okay. I feel like this is just regular class now. No one wants to answer.
Time is changing.
Time is changing. It's doing what?
Slowing down.
Slowing down. So when you go really, really fast, time starts to slow down. And this is actually one of the things they have to account for with GPS, because those satellites are up there. GPS is essentially a very, very accurate timing system. All right? And so while those satellites are going and orbiting that high, they actually have to adjust for their speed being so fast that their clocks are running slower than ours down here on Earth. And so they adjust for that in order to keep the correct time with what's down here on Earth, and therefore you can find where you are. All right? Timing is very important for GPS. Now, let's think of this a little further. Okay? Let's take our same situation, person on the train. Actually, I might move that over. Person on the train, and the person on the train thinks, I'm standing still here, right? And this time, let's give our light clock to the person on the side here, you on the side. Now you have the light clock, you have the mirror up here, you have the laser light you're going to shine straight up and have come straight back down and time isn't it. And in fact, it could be happening at the same time the person on the train was doing their light clock as well. Now, you on the side of the road, on the side of the train track there, you do the same exact time clock, same exact thing, up and back down. Now your stopwatch reads 2 seconds, or 2 units of time, whatever it happens to be, right? But think of it from the perspective on the guy on the train, who has every right to say he's the one that's still, and the guy on the side of the tracks is the one that's moving. When he looks at the guy on the side of the track, he sees the guy on the side of the track going off that way away from him. He's going to see the angle light, isn't he? Mm-hmm. From his perspective, he's going to say, oh no, I timed that same event. You know, we have the same speed, except he thinks that that guy's going this way at speed v instead of him. He comes up with the 3 units of time. And they could both do this at the exact same time. They could both have the light clocks going with 2 stopwatches going, timing each other's light clocks. The guy on the side of the road says the guy on the train's time is running slower. The guy on the train says, no, my time's running normal. The guy on the side of the tracks' time is running slow. They both think the other is running slow. So who's correct? Yes?
If train is moving same speed as a light, what happens in both cases?
Oh, we'll get to that. We'll get to that eventually. We will. We'll get to that idea. It was one of the things Einstein thought about, where the idea he gave was is if he had a mirror, and he started accelerating, and what would happen if he was looking at himself in the mirror if he started going with the speed of light? Like, would the light from his face, would he be able to see in the mirror anymore? So we'll get to that. We'll get to the whole idea of going the speed of light. Okay? It'll turn out, spoiler alert, you can't do it. All right? But we have 2 disagreements here. So let's take this to a more extreme example. Let's pretend this is called the twin paradox. All right? This is a big paradox in physics, and we're gonna basically today I'm gonna give you a bunch of problems, and then later on we're gonna figure out solutions to them. So let's pretend that we had a set of twins, and one of them stayed here on Earth. Put a big E for Earth, so we know. They stayed here on Earth, and the other twin gets in a rocket, and they fly away from Earth. There's a fire coming out of the rocket engine. They're on the rocket, and they fly away at a speed really, really fast, near the speed of light. Okay? Now, the twin that stays on Earth watches their sibling go off at near the speed of light, and as they watch them, they see them moving slowly. They see all their stuff going more slowly, all their light clocks running more slowly. The twin on Earth says, I'm aging faster than my sibling. Right? And so now I'm going to be the older twin. So if they go off for a long period of time, and say it's like 10 years for me, it might only be 1 year for them. But what if we look at it from the perspective of the twin on the spaceship? The twin on the spaceship says, I'm staying here, and I watched my sibling and Earth zoom away from me really fast, near the speed of light. My time kept going, all their clocks slowed down. For me, it's been 10 years. For them, it's only been 1. We bring them back together, somebody's got to be older, right? Or they have to be the same age. There has to be a result to this, correct? But we have a disagreement here. They each think the other is wrong. So which one's going to be right? When they get back together, is the one that stayed on Earth going to be older, or is the one that went off in the spaceship going to be older or younger, or they're going to somehow end up being the exact same age and didn't even work that way? I'll give you a hint. They won't end up being the same age. I guess there is a way you could do that, but they won't end up being the same age. Okay?
It depends on how to measure time.
Light clock. We're all using light clocks to measure time. But if your light clock slows down, then all your intermolecular processes slow down, and everything slows down. So even normal clocks should slow down. Electrical circuitry slows down, everything will slow down. Okay? A little interested yet? Okay, all right. I know it's a little slow start, but there's the twin paradox, right? This is a big one. And there was that old movie Cocoon. Anybody ever see that? Old movie where these people went off in outer space and they came back here and they were still young. But we'll get to that. All right. The next thing we want to talk about is length contraction. This is another result of relativity, of something that happens. When something starts moving very fast relative to you, it starts to shrink. Okay? It shrinks and it gets shorter and shorter. Now, there's an equation for this. I'm not going to derive it for you. You're welcome. But it's basically says this: a change in the prime position is equal to gamma times a change in the unprime one. So a change in the moving coordinate system is equal to gamma times a change in the stationary or your coordinate system, which we can just say a change in position like that. We can just call that length. L equals gamma, or L prime equals gamma L. And so what this tells us is when something is going very fast relative to you, it gets shorter in the direction that it's going. So if there was a meter stick flying by really, really fast, and just as it passed you, you held up your meter stick, you would see that that flying by meter stick was shorter than your meter stick. Even if before you left, you put them together and found they were the same length. You get this length contraction that occurs, all right? And this brings us up another interesting problem. This was my favorite one. It's the ladder in the barn. And the idea is this farmer finds that the ladder that he has is too long to fit in his barn. So he decides he has a daughter that's really, really fast. So he tells her to grab this ladder, right? He says, okay, here's the barn. I'm going to stand by the barn with the door open. There's the door, it's open. Okay? And when you come by running really, really fast, I want you to run so fast that even though this ladder, is longer than the barn, I want you to length contraction it. All right? I want you to run so fast that it squishes its length down, and so that the ladder is now shorter as she's running it into the barn. And as soon as you get in there, I'm just going to slam the door shut. Okay? Well, what's going to happen here? It's short enough now to fit in there, but is that going to actually work? This is another one of these problems we'll talk about later, right? There's also other ones you can find examples where they talk about a train going really fast through a tunnel, and you close the train in. Even though the train is longer than the tunnel, the train is going so fast that it fits inside the tunnel at once, and then you close it in. You like shut the doors at both ends. What's gonna happen? So,
Train crash.
yeah, train crash. I did actually forget one thing I meant to show you. I gotta go back here, because I went off on that other page. And that was what the actual equation was for this time dilation. This is called time dilation. And we can do it just with geometry. Pythagorean theorem. Not too bad, right? A squared plus B squared equals C squared. So we're gonna not go any worse than that. So let's draw this situation in. For the person on the train, they see the light go up and come back down. For the person on the side, they see the light go at an angle and then come back down. And this gives us two right triangles. You see them there? Two right triangles. Now, the length of the right triangle's two sides, this first one is velocity times time. So it's simply the speed of the train times the time that the train is traveling. All right, however long it took for the light to go up. Then, from the person's perspective on the side of the road, this side over here, this hypotenuse part, that's the light they see. It has to be going a speed of c, and also has to take that same amount of time, t. See that? Now, as far as this other leg goes, this person thinks they're sitting still, and all they're doing is watching light go straight up and come back down, so they see speed of light times their time, t prime, as they're moving. Okay? Now, we can just simply go through. I need a little room here. That's not erasing. Or it is very slowly. Okay? We can do Pythagorean theorem. We can say v squared delta t squared, that's that first leg, plus c squared delta t prime squared equals c squared delta t squared. All right, and from this relation, I will skip some steps here, not show you all the algebra, go through and do the algebra. What you will find is that you get delta t equals delta t prime times, and what you end up with is this delta t prime equals delta t times 1 over the square root of 1 minus v squared over c squared. Does that 1 minus v squared over c squared thing there look familiar? Remember that from a few minutes ago? That's gamma. So gamma just falls right out of doing just regular old Pythagorean theorem. It actually just shows up. So much like the one for length, all we're really doing is just multiplying by that gamma factor to tell us how much of a difference between the two times there will be. We doing okay so far? Do I need to slow it down, speed it up, anything? No, we're okay? Okay. I got like a couple of people to give me thumbs up. So there we go. All right. So there was our equation for length contraction. We have an issue with this. All right. So let's talk about this let's do an actual example of these things. Muon decay. So muons are these really heavy electron-like particles, and they get created a lot in the upper atmosphere. Now, their life cycle is just a couple microseconds. It's not very long. And the speed at which they travel and how high they start up, a couple of microseconds is not enough time for them to reach us here at the surface of the planet. But they do. They do reach us here at the surface of the planet. In fact, if we had a muon detector, we could go outside and you could start detecting them. They do reach us from the upper atmosphere. How can something make it down here before it goes away and decays, right? if it's not going fast enough to get to us? Well, the answer to this is one of these two things: time dilation or length contraction. So from our perspective, we would see these muons traveling really, really fast. And therefore, we would find that their clocks are running slow. And therefore, what appears to be 2 microseconds or so to them is actually much longer for us. And so they can reach us because we would say their clocks are running slow. It's taking a lot longer for 2 microseconds to run by for them than it is for us, and they reach us. From their perspective, however, their clocks are running just fine. So from their perspective, if you were riding right along with one, the thing that would happen is not time dilation would not tell you that you reached the surface of Earth because your clock is running just fine. What would happen for you is that's the direction you're traveling is your distance from the upper atmosphere to the ground is a lot shorter. It length contracts. So from their perspective, they're traveling a shorter distance. From our perspective, it's their clocks that have slowed down. But we still end up with the result that they reach us here at the surface of Earth, even though without this idea, without this time dilation idea, they wouldn't. Okay, so that's a pretty well-known example of this stuff. Okay, so the next thing, correlation and causation. I'm going to try and break this now. And this is I even bolded it. This is very fundamental to science, right? I mean, this is what you do. You do event A, then you do event, and then you watch for event B. And if every time you do event A, event B follows, you start to think event A has some sort of causal link to event B. Like, I have a jar of baking soda, and every time I pour vinegar into it, bubbles come up. So pouring vinegar into baking soda makes the bubbles come up. Okay, because every time that's the order that happens. It's not like you go to pour it in there and it starts bubbling ahead of time. It bubbles after you do it. So the ordering of events, very, very important to science for us to be able to come up with a correlation, right, and start to see that two things may actually be related to each other. They might actually be causing each other. I mean, it might be once, like, I remember hearing a story about a guy who thought he found a way to use sunlight to break water apart into hydrogen and oxygen. All right, but it turned out it was just coincidence. He happened to walk out in the sunlight at the time it started bubbling, but he walked out in the sunlight and immediately it started bubbling, and he was like, "Oh my gosh!" He thought he accidentally found this and was going to be like crazy rich, but every time he tried it all again, it just turned out it did it after the same amount of time every time. It wasn't what he originally thought. So correlation doesn't necessarily mean causation, but if we don't have correlation, we sure don't have causation. Okay? So if we're getting bubbles before we pour the vinegar, then we're not going to say the vinegar is causing the bubbles, right? So let's take a look at some lightning strikes. I'm going to set up a situation here. We're going to stand right in the middle between 2 lightning rods. Lightning rod, like that. And we're equidistant from both of them. And then we're going to stand here and we're going to look at a mirror. A wedge-shaped mirror that's right there from both of them. And from this first person's perspective, let's go ahead and call this one over here. We'll call this A and B, just to make it a little easier to talk about. This poor guy needs arms. Okay. So you look at this wedge-shaped mirror and you can see each of the lightning rods at the same time, like one with each eye. And so lightning comes and it strikes. No, I did not take art lessons. But there's the lightning strikes, and it strikes them both at the same time. And so the light comes from this one, hits this, bounces off, goes into his eyes, and it takes it the same amount of time for the other one to do it. And he looks and he sees both lightning strikes happen at the same time. Okay? He says, hey, they struck at the same time. There could be no causal link between the two because they happened. Lightning strike A and lightning strike B happened at the same time, and therefore they couldn't have caused each other because they were simultaneous. But let's add another person in. And this person is moving, right? And we'll give them the same sort of situation. They have this same little wedge-shaped wedge-shaped thing here. I kind of ran myself out of room, but they're over here looking at this, moving with their mirror that way, at some velocity v. And then the lightning strikes occur. Now, as the light is traveling from here towards this person's mirror, right? They're moving. So by the time the light from B reaches them, they've already moved to the right some. And the light from lightning strike A hasn't reached to them yet. So they're going to see lightning strike B first as they continue moving off to the side. And they say, oh, B was struck first. And then as they continue moving over, the lightning strike from A is eventually going to get there, and then they're going to see A. So here, they saw B strike, then A get struck. From their perspective, they saw B, then A. And in fact, if we keep doing this, they're going to see B, then A, B, then A, B, then A. They're going to start to build a correlation and say, hey, lightning strike at B could be causing a lightning strike at A. Maybe there's some connection or something there that makes the lightning want to strike over there after it strikes here every time. And so they disagree about the order of these events. Now that's a problem too, right? Because one person seems like they're building up a correlation, which is like they can do some science on it. The other person is saying, no, they can't cause each other. What if we had a third person go in the other direction? You have another person go, they'll say A happened, then B happened.
The distance are same? The difference A to person, B to person same?
Sure, that wouldn't matter.
But that distance is too short then.
Because that part doesn't matter. You want me to move.
At the same time?
You want me to move this, if I can, I don't know why it doesn't want to erase. You want me to move this other guy further back? Is that what you're saying? It wouldn't make a difference for what order you saw them in. We've been just disagree on like what time they both occurred on, but we were already disagreeing on time. But you can move them further back. All that matters is which one happened first or second. Both of these people have the right to claim they're still. Both of them have to have the rules of physics be the same for them. That's according to our postulates and all of our experimentation. We've never been able to find the speed of light to be different. Yet, they're disagreeing on the ordering of events here. Now, if we were to stop there and not keep going on, that'd be an issue, right? Because at this point, we've kind of broken our ability to correlate events. Therefore come up with causation, and therefore really just do any kind of science. If we can disagree on the order, I mean, this is something like if we were in intergalactic space waters or something where like one guy says, oh, I saw the ship fire the missile and then the planet blew up. But another guy goes, no, that planet blew up before they fired the missile. Like, do we go to war or do we not go to war over this unprompted attack, right? Like, I mean, this can be a big issue, right? I mean, on our everyday life and our everyday scales, we move so slowly compared to light that we don't notice these differences. You know, if we were trying to do the twin paradox, if you got in like the fastest airplane and you flew around in it for the rest of your life, you'd add like a fraction of a second onto your life. We are so slow compared to light. But when we get to really, really fast situations, this starts to become a big issue, all right? And it's at least a little issue when it comes to other things. I have been blabbering on now, it looks like, for about 50 minutes. So I'm going to stop at that point. I'm gonna leave you with lots of questions to hopefully entice you to come back. And I'm gonna see if anybody wants to ask me anything. Yes?
Is the main point that everything is just relative, so we have to find some way to measure time, and so we're deciding to measure time based on movement according to ourselves, so it's now individual time, and that's how we can get different time?
Basically, but then that's kind of a big problem because a result of that seems to be that we're disagreeing about things happening.
Yeah, but I'm just thinking with the twin paradox, like even if we do take this measurement of time, with the time clock, okay, so he goes, he comes back, they have disagreement.
Oh, I never said he came back.
They go away. They never come back.
Oh, you're getting ahead of me there. we haven't
Yeah.
encountered that yet.
Yes, but so they have their time clock and
Uh-huh.
so they measure themselves, and then one twin says, okay, I'm officially 10 years older than you, according to my time, my individual time, relative to how I also measure your time. And so he decides he's 10 years older,